Hello everyone, welcome to Prince on Air, and we are back with another video that is of solid state imperfection in solids. Okay, all of you know about that whenever you are looking at anything, okay, which is having regularities, they are not in actually regular. Okay, they will have some sort of imperfections. Nobody is perfect. Okay, so similarly in solids also there will not be any perfectness. Okay, there will be some imperfections. Clear? So in solid state we will discuss about the imperfections in solid and types of imperfection that we will discuss here. Okay, so that is a very interesting topic, and actually it is a theoretical based topic, and that we have to just listen carefully and just we have to enjoy this topic. Okay, clear? So let's start without wasting any time. Open your notebooks and pen and make that note side by side here. And some students were asking that question related to the numerical portion, the last numerical portion. That one question was asked by a student that I have given to you. So even I have given the solution, even I have given the answer of that question. Okay, so now that I have replied that answer of that question, so you can check out. And some students are asking the questions related to the polycrystalline solids. Okay, so what are polycrystalline solids? Listen carefully. The crystalline solids are what? Crystalline solids are what? Like which are having regular arrangements. Okay, but in crystalline solids, if we are having small types of crystalline solids, okay, means which are having, in that section they are having a regular arrangement, but when they are arranged in together, they are in the random form. Okay, means totally, actually if you are looking at the whole, they will behave as a amorphous solid. Okay, they are not considered to be as the you can say crystalline solids. So actually they are made up from the crystalline solids, but their actual arrangement is deviated. So actually they are made up of crystalline, so that's why we are using that word polycrystalline solids. Okay, basically the metals are crystalline, but when the smallest portions of the crystalline metals are arranged, and they are forming the random arrangement. Okay, so they will form the characteristic related to the amorphous. So that's why they are just related to, they are considered to be as a polycrystalline solids. Okay, poly means many, crystalline means crystals. Okay, so polycrystals means many crystals make that polycrystalline solids, and majority of the metals are behave like this. Okay, okay then. Now imperfections in solids. Okay, as we have discussed that crystalline solids are not perfect. They have the defect when their crystallization occurs. Means whenever there is the formation of crystallization, okay, crystallization may occur from the amorphous to crystal. Okay, means the formation of crystals from amorphous, that we have discussed now with the process of annihilation, of annealing. So in that way, whenever there is a formation of crystals, okay, that process may be fast, moderate or slow. During that process there will be some irregularities or imperfection occurs, okay, during formation. So the defect occurs when there is a formation of crystals, or you can say the crystallization occurs. Okay, basically defects are irregularities in the arrangement of particles. As we know that particles are regular in shape, regular in arrangement in crystals, but some sort of irregularities will be there. Okay, so that we will discuss here also in the case of imperfections in solids. Yeah. Now defects are of two types here. Okay, in solids we will discuss about the two types of defects, and basically we will discuss only one type of defect in detail in these sections. Okay, is it clear now? Two types of defects we will discuss here. First one is point defect, clear, and second one is line defect. Point defect and line defect, clear. Two types of defects we will discuss here, point defect and line defect. and in detail we will discuss about the point defect. Okay, in detail. Clear? So what are point defects? The irregularities, obviously the defects are irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance is known as point defect. Now you can see from the picture here. Okay, see from the picture here. Here we have some sort of defects here. Okay, here you can see that arrangement of particles of the blue particles, then purple, then blue, then purple. Now you can see that there is a different type of particle here. Okay, can you see this? Yeah, that is just in between the actual arrangement of particles, or you can say in place of one blue particle. That's occur now. So it is showing the irregularity. Clear? Similarly, here you can see these particles are missing. Okay, clear? So these types of irregularities are of a single or two more than one particles. Only particles problem is there. Okay, or irregularities in the particles are there. So that's why it is known as point defect. Okay, it is known as point defect. Okay, then if there is a irregularity or deviation in full line, okay, then it is known as line defect. The irregularities or deviation from the ideal arrangement in entire row of lattice, then it is known as line defect. Okay, here you can see, actually this picture you will not see in the big book, so you can see here. So whenever you are looking at this line, see here that particles are missing. Okay, so that's why it is known as line defect. And in detail, in your this standard or according to your syllabus or book, we will follow only the point defect. We will discuss the point defect in detail. Okay, so let's start. Yes, so types of point defect. Here we will discuss about the types of points defect. Okay, so there are basically three types of point defects. First one is stoichiometric, then impurity, then non-stoichiometric. Firstly, what is the meaning of stoichiometry? Sometimes some are using that word stoichiometry. So actually stoichiometry. So what is the meaning of stoichiometry? Actually it is the proportion of the given components present in a given molecule or given formula, like NaCl. What is the meaning of NaCl here? It means the Na1Cl1 means the ratio of sodium and chloride ion are 1:1. Okay, means if the n number of ions of sodium are there, then n number of ions of chloride ion will be there in a given lattice. Okay, so that is the meaning of this formula. Okay, so stoichiometry means the you can say understanding of their formula basis. Okay, or you can say their ratios of proportion ratios. Okay, so here impurities, as you all know, we will put some external components in this case. Non-stoichiometry, that all components are related to each other, and that we will discuss in the later on. Later means in this lecture, actually in the next part. Okay, next slides. Clear? Now firstly we have to discuss about a stoichiometric defect. What is stoichiometry? See, stoichiometry means in which no stoichiometry will be disturbed. Stoichiometry defect, no stoichiometry is disturbed. See carefully. Get out. Get out means get in. Okay, that thought you have to get in your mind. Stoichiometric defect means there should not be any change in the stoichiometry. Okay, means the ratio of the components present in a crystal or lattice should be same. Okay, clear? So we can take that one more example in this case, as I have given to you now. NaCl, if one ion of Na positive is removed, similarly in that case of chloride ion should be removed. Okay, so in that way the total ratio of both ions will be same. So in that case we just see the stoichiometry will not be disturbed. So now see the definition of or the components here. These are the point defects. Okay, actually it means point. Okay, point defect that do not disturb the stoichiometry of the solids, and these are also called the thermodynamic defect. That is most important here. Okay, because these defects are occur when you are applying external heat to the crystal. Yeah, whenever you are applying external heat to the crystal, then these types of defects are observed. Clear? So here thermodynamic defects are the defects whenever you are applying external heat to the given crystal. Okay, so these types of crystal are also called the thermodynamic defects. Okay, so these are of two types: vacancy defect and interstitial defect. Okay, vacancy defect and interstitial defect. Here you can see that vacancy defect means there will be a vacancy of the particle. There will be a vacancy of the particles, means one particle is removed from here. Okay, one particle is removed from here and it will form a vacant space. Okay, so that's why it is known as vacancy defect. Interstitial impurity, it means one particle from external source. Okay, one particle from external source comes to the interstitial space and occupy that space. Okay, so that is known as interstitial impurity or interstitial defect. Okay, clear? Here you can see that the particle is moving from the one position, okay, and it is forming a vacant space there, and it is also occupying the interstitial points. So both defects collectively are occurred in this the particular crystal here. Okay, so both defects you can see in this case. Now vacancy defect. Okay, what are vacancy defect here? Actually, with these defects we are discussing only for the non-ionic crystals or solids. Okay, non-ionic solids. These are for non-ionic solids. Okay, afterwards we will discuss about the ionic solids. So when some of the lattice sites, listen carefully, when some of the lattice sites are vacant means empty. Okay, the crystal is said to have vacancy defect. Okay, means whenever there is an empty space, like here it is a perfect crystal. It is a perfect crystal here. So whenever that particles, you can see this particle is removed from here, you will see this will occur. Okay, means vacancy will occur there. So it is known as vacancy defect. Clear? Now the results in the decrease in the density of substance. Means when what is density? Density, mass over volume. Yes or no? Mass over volume. So in this case, mass, actually the particle is removed. No, the actual mass of the crystal will be decreased. So if the mass is decreased, then density will also decreased. Okay, so in this case, in this particular case, that is most important point here. Sometimes in MCQs they can ask you that question later on there. So if the density is decreased, in this case the particles are removed. No, so that's why the density is decreased here. This defect can also be developed when the substance is heated. Okay, similarly it is also a thermodynamic defect. Okay, clear? Now interstitial defect. Interstitial defect we have to discuss here. What are interstitial defect? When some constituent particles are occupying the interstitial site. Interstitial site means the in-between site. Okay, in-between site. What is that in-between site? For example, when in a bench, in a single bench, two students are sitting, and one student is coming outside from the class and sitting just in between them. Okay, so that is the interstitial site. Similarly here, these all sides are interstitial. Okay, so whenever that particle is coming here, like here you can see, okay, it is a perfect crystal. In this case, the particle is coming out from here, outside from outside and occupying that place. So in that case, that is known as interstitial site, and that occupying the interstitial site, and that defect is known as interstitial defect. Okay, so when some constituent particles occupying an interstitial site, the crystal is said to have the interstitial defect. In this case, here we are supplying some external particles to the crystal. In this case, the mass of the substance or the mass of the crystal is increased. So density is, once again, density is mass over volume. Okay, so if the mass is increased here, if you are supplying externally any particle, mass is of the crystal will increase. In that case, the density will also increase. So in this case, the density of the substance increases. Okay, clear? Okay. Now, Frankel defect. Now these defects, Frankel and Schottky defect, these defects are only for the ionic crystals. Clear? These defects are only for the ionic crystals, and for these are the most important defects that we have to discuss here. Okay, because so many times in your exam they can ask you question, and CBSE is asking question related to the topic. Okay, related to Frankel defect and Schottky defect both. Okay, I'm just telling you one more thing here. In chemistry, no, students are just going away from the names of scientists, and all the examination centers and examination criteria, they just forcing the students to just memorize the names of scientists. Okay, so how they are just giving that criteria? By giving that question in your exams. Okay, so nobody knows about the Frankel. Okay, because in chemistry the scientists are not so famous. In physics they are famous, like Newton, Einstein, all are famous here. But in case of chemistry, some except from the some scientists, many of the scientists are not actually got that famous, that fan following as in physics. Okay, so what the examination criteria are following, they will give you the questions on the names of the scientists. Okay, so that you have to learn that names of scientists, okay, names of the chemists also. Okay, so that's why. So the defect is shown in ionic solids only. Okay, this type of defect is shown in ionic solids. And listen carefully, in this case the smaller ion is dislocated from the normal side and to the interstitial side. Okay, clear? Means in this case the smaller ion is of positive charge or negative charge? Yeah, sure, positive charge. Positive charge are of smaller size, and negative charge are of bigger size. Okay, so always the positive charge, the smaller ion is dislocated, means the cation will dislocated. Okay, cation will dislocated from its normal side to an interstitial side. Okay, clear? Now it creates a vacancy whenever the smaller ion move from its own position, so it will create vacancy there. Okay, at its original site and at interstitial defect is the new location. See here, you can see here, you can see that this one is carrying positive charge and this one is carrying negative charge. Okay, now this one is going from here to here. See this, so it is occupying that interstitial site here. Yes or no? So similarly what we have discussed, that is happening here. So now what they are saying, that it creates a vacancy defect. Vacancy is created here. See that vacancy is created here. Okay, at its original site, and the interstitial defect at the new location. Means, see, interstitial defect is observed here. Yes or no? Yes. Okay, so it is called the dislocation defect. Okay, that is most important part. Why Frankel defect is known as dislocation defect? Okay, so answer is this line. Okay, it creates vacancy defect at original site and an interstitial defect at its new location. So in this case, only the smaller ion is dislocated from the normal side to an interstitial side. Okay, these two lines is the answer of this question, why Frankel defect is known as dislocation defect. Okay then. So in this case, no externally particle is supplied and no internal particle is removed, so no change in density will occur. Okay, so there will be no any change in density. Okay, so it is shown by the ionic substance that we have already discussed. Frankel and Schottky defect will be shown by ionic solids. Yeah. Okay, so in which there is a large difference in the size of ions. Large difference in the size of ion, that is the most important point here. Clear? Whenever the cation size is smaller and anion size is bigger, if the cation size is smaller, anion size is bigger, means anion is bigger here, so they will have more vacant space here. In that way, if the cation size is very smaller as compared to anion size, then it will be easy for the cation to occupy the interstitial state or interstitial space. Okay, so to occupying the interstitial space, the size of cation should be very smaller as compared to anionic size. Okay, so that is the main point here. And examples of this defect are, that is the crystal which are showing this type of defect are zinc sulfide, AgCl, AgBr, AgI. Okay, remember that AgBr here. Okay, that I will tell you why we are I am focusing on AgBr here. Okay, so is it clear now? Now let's move to the next, Schottky defect. What is Schottky defect here? It is basically a vacancy defect in ionic solids. Okay, it is basically a vacancy defect in ionic solids. Clear? In order to maintain, listen carefully, in order to maintain the electrical neutrality, the number of missing cation will be equal to number of missing anions. See here, you can see that this one is negative charged ion, means anion, it is positive charged cation, so both are missing from the crystal. Okay, both ions will be removed from here and they will form a vacancy here. So it is actually a vacancy defect, no doubt. To maintain the electrical neutrality, firstly you can say you can remove the positive ion, then negative ion also, because to maintain the electrical neutrality, if you will remove the positive ion, suppose if you are removing one positive ion, so there will be a negative charge on crystal, and if you are removing negative ion, there will be a positive charge on crystal. So to maintain the electrical neutrality, both ions will be removed. Okay, clear? Yeah. So in this case, both particles are removed from the crystal, mass decreased. Okay, mass of that crystal will decrease. So in this case, the density will decrease. Okay, in this case, the density of the substance is decreased. It happens in those ionic substances in which the size of ions are of similar size. Okay, it will happen. Okay, that is the main point here, and in the differences we will discuss about it. It will happens in those substances, those ionic substances in which the ionic size is similar. Okay, example is NaCl, KCl, CSCl, AgBr. AgBr. You can see that AgBr here also and here also. See, so means Frankel and Schottky both defects are shown by AgBr. Okay, silver bromide. Clear? Now the difference between Schottky and Frankel defect. Okay, the difference between Schottky and Frankel defect, that we have to discuss here. Now let us discuss about that, the difference between Schottky and Frankel defect. Okay, so Schottky defect, firstly we have to discuss about the Schottky defect. First, when oppositely charged, see, oppositely charged ions leave their lattice sites. Okay, means vacancy will create. Okay, when vacancy is created. Okay, afterwards I will give you the trick how you can memorize, just memorize the both defects. Okay, Frankel. Okay, smaller ion. See that smaller ion, usually cation. Okay, usually cation displaced from its lattice position to the interstitial site. Means it will occupy, it will create vacancy also, and it will occupy the interstitial site also. Means both type of defect will occur in this case. Okay, then these vacancies are formed. These vacancies are formed in stoichiometric unit to maintain the overall neutrality charge. Okay, overall neutral charge on the ionic solid. But in case of this, in case of this, create a vacancy defect at its original site and an interstitial defect at its new location. Means both type of defects will occur in this case. Here density will decrease, but here density is not changed. Okay, density is not changed. Occurs only when there is small difference in the size between the cations and anions. Schottky defect occur when there is a small difference in the size of cations and anions. But in case of Frankel, the size of cation should be smaller than the anion, or you can say that there should be a large difference between the size of anions and cations. Okay, so that is the actual difference between the Schottky and Frankel defect. Now, how you can memorize that? Okay, some students are doing that mistake. Means they know very well these type of defects are occurred in ionic solids, and they know that what is Schottky defect, what is Frankel defect, but they usually in exam they are just intermix these both. Like in place of Schottky defect they are writing Frankel defect, and in place of Frankel defect they are writing Schottky defect. So how you can balance between these two? Okay, so I will give you that trick how to bring out from this sort of problem. See, Schottky and Frankel. Okay, so all of you know about that period, huh? That is the lockdown period here, huh? Yes or no? Okay, so in that case, if we are going to school, okay, if we are going to school, means in school, what I am saying, listen carefully. Here I can explain, huh? In school, if you are going in school now, you will be fine. Okay, you will be fine. So school, it means Schottky. Okay, in means interstitial. F means Frankel. In means wait. In that way you can see school and fine. Here you can see that. In this case, Frankel defect and Schottky defects are occur, no? Yes or no? So actually in Frankel defect, what happened there? Vacancy occur in the Schottky defect, and Frankel defect there will be the dislocation. So what you will see, into the students I have given that trick, that is just you have to write that fine, okay, fine in vacant school. Okay, fine in vacant school. Okay, so fine, F for Frankel. I was writing just opposite. Interstitial, or from here you can see interstitial. Okay, vacancy, and from here Schottky. So now Frankel will show interstitial defect. Okay, Frankel will show interstitial defect, means it in this case the one particle will leave its position and it will occupy interstitial site. Okay then, and in this case Schottky will show vacancy defect. Clear? In ionic solids. Okay, so in this way you can understand. Okay then, now impurity defect we have to discuss here. What is impurity defect? See, impurity defect, clearly NaCl crystal we are having here. So if we are adding some external components, externally if we are applying some adding some ions, okay, and that type of ions should be different from the original ions which are present in crystals. Okay, that is known as impurity defect. Okay, for example, this is a crystal of NaCl, and if we are adding strontium ions, Sr2 positive ions, Sr2 positive ions, that Sr2 positive ions are just equivalent to the 2 Na positive ions. To maintain the electrical neutrality, we can add one Sr2 positive ion in place of 2 Na positive ions. So here you can see it was Na positive ion here and also Na positive ion here. So whenever we have added the Sr2 positive ions, so 2 Na positive ions will be removed and one Sr positive 2 positive ion will occupy at the position of Na positive ion. Okay, so one vacancy will also be observed here. Clear? So that type of defect is known as impurity defect, and that you can see or visualize in this form. See it carefully. Okay, so now see, this one is the ion, that is Na positive ion. Okay, it is impurity here. Here we are just considering it is impurity. Now if you will see that Na positive and Cl negative ions here, the formation of sodium and chloride ion, and here strontium remove the two Na positive ions here, and here there is a formation of vacancy. Okay, now non-stoichiometric defect we have to discuss. Non-stoichiometric defect are those defects in which they will disturb the stoichiometry. Okay, they will disturb the stoichiometry of the substance or crystalline substance. Okay, clear? Means in which the ratio of the ions will not be similar, okay, or equal, or you can say balanced. So here these are of two types: metal excess defect and metal deficiency defect. Okay, metal excess defect and metal deficiency defect, that we will discuss in the detail now. So what are metal excess defect? Metal excess defect, see, in this case you can see that there will be the existence of positive ions or metal ions in greater amount as compared to the others. Or metal deficiency defect, that we will discuss here also. Actually, what are metal excess defect? These are further classified into two categories: metal excess defect due to anionic vacancies and metal excess defect due to the presence of extra cationic interstitial sites. Okay, means when there is a presence of extra cations at the interstitial site here. Okay, then now we can see this here. Some metal excess defects are observed. Okay, and in this case metal excess defect is due to extra cations, means extra cation is here, no? Okay, so here the cation will occupied at the interstitial site, or you can say extra cations are observed. But one more is there, that is metal excess defect due to the anionic vacancy. Anionic vacancy is there, and in this case the electrons are observed here in place of anion. Okay, so anionic vacancy is there, but in that place one electron will be there to maintain the electrical neutrality. Okay, now metal excess defect due to anionic vacancies, that we have to discuss here properly. So alkali halides like NaCl, KCl, they will show this type of defect here. See, one clearly you have to just imagine that is a NaCl crystal. For example, this one is a NaCl crystal here, and when it is heated in the vapors of sodium, okay, sodium vapors, in the presence of sodium vapors, in the presence of sodium vapors, in the presence of sodium vapors, when it is heated, okay, when it is heated, there will be removal of chloride ions from here, Cl negative ions. For example, here it is sodium, okay, sodium atom I am saying, and chloride ions will remove from here and it will bind up with the sodium atom, and in that case sodium will remove one electron, okay, it will remove one electron and it will form Na positive ions, and that Na positive ion will bind with the Cl negative ion, and that electron will come to the chloride ion place, okay. So now you can see that properly, that electron is occupying the position of chloride ion, clear now. So this defect is known as metal excess defect due to anionic vacancy. Anion is removed now, so that there is a vacancy for anion, okay, and their position occupied by the electron here is known as what it is known as, okay, can you tell me the name of that particular center? It is also known as F center, okay, it is also known as F center, okay, it is also known as Farben center, or you can say only F, in short you can use that word F center here, okay. Then is it clear? Metal excess defect due to anionic vacancies, okay. And remember that which type of solid it will show this type of defect, that is alkali halides or alkali halides like NaCl and KCl, okay. Then okay, so now one more defect is there, that is metal excess defect due to presence of extra cations at interstitial site. Now what type of defect is this? See, in this case the zinc, here you will see that zinc oxide, okay, zinc oxide, whenever zinc oxide is heated, okay, whenever zinc oxide is heated, it will form zinc 2 positive ions and half molecule of oxygen, and 2 electrons will be removed, okay, 2 electrons will be removed, and that electrons are occupying that positions, that interstitial positions, okay, and in that way the zinc positive ion is formed here. All are of zinc positive ions, but here zinc 2 positive ion is formed here. So due to presence of these free electrons and the movement of these electrons and also that of ions, actually zinc oxide is of white in color, but it will form yellow color substance, okay, it will form yellow color substance. So the question is there, why zinc oxide on heating changes into the yellow color? That is the reason here, because it is showing the metal excess defect due to presence of extra cations at interstitial site here, okay. So they are occupying the extra sites, cations at the interstitial sites here, okay, clear now. Now one more type of defect is there, that is metal deficiency defect. See carefully, one more point is here. Have you seen the formula FeO, iron oxide, okay. In that case iron and oxygen, the ratio should be same, but in actual it is not same. Their ratio is like in this way, Fe 0.94 to 96 and O1, that is the actual ratio here. Now why it is so? See, here iron is a mixture of both types of iron, Fe2 positive and Fe3 positive, ferric and ferrous ions, okay, both types of ions are there, Fe2 positive and Fe3 positive. So if you are making the crystal, Fe2 positive will combine with O2 negative, obviously, okay, but in some cases there will be oxygen will carry 2 negative charge, but in some cases in 2 Fe3 positive will be just equivalent to, see carefully, 3 Fe2 positive. Okay, 2 Fe3 positive will carry 6 positive charge, and 3 Fe2 positive will carry 6 positive charge. So they, to maintain the electrical neutrality, some of the Fe2 positive ions are replaced by Fe3 positive ions. So in that case, the number of Fe ions, just I am saying Fe ions, iron ions, okay, they will be decreased. So that's why in actual the ratio of ions are less, or you can say metals are less. So that's why this defect is known as metal deficiency defect. Now here you can see here, FeO heated on in oxygen atmosphere. So actually the X is less than 1. Okay, here oxygen is 1, X is less than 1, means the value of iron ions will be less than 1. Okay, or you can say less than the number of oxide ions. Okay, so vacant cation sites are present. Here you can see that vacant cation sites are present there, because Fe3 positive ion is present and only Fe2 positive ion is required, one will be left. Okay, so here this effect is happened, their charge is compensated by the conversion of ferrous to ferric ion. Ferric ion is Fe3 positive ion and ferrous ion is Fe2 positive ions. Okay, so for every vacancy of Fe cation, 2 ferrous ions are converted into ferric ions. 2 ferrous ions are converted into ferric ion. Okay, clear? Means in place of 2 Fe2 positive, you can say 2 Fe3 positive, 3 Fe2 positive. Okay, so they will compensate the charge. Clear? Is it clear now? So in that case, the charge is neutral, charge is balanced, but the number of metal ions will be decreased. So that's why it is known as metal deficiency defect. Okay then, clear? Now metal excess defect due to presence of extra cations at interstitial site, that we have discussed here. So that is the end of this lecture here. So thanks for watching this video, and once again I just want to read one, you can say that share. I've just read about that share just now. Actually it is on the, you can say, actually this is the end of this video. Okay, if you want to move, you can move it. I just want to give you the share and just want to show you. Okay, so गुजर रही है जिंदगी अब ऐसे मुकाम से, गुजर रही है जिंदगी अब ऐसे मुकाम से, अपने ही दूर हो रहे हैं जरा सी जुकाम से. सी केयरफुली, गौर फरमाइएगा. गुजर रही है जिंदगी अब ऐसे मुकाम से, अपने ही दूर हो रहे हैं जरा सी जुकाम से. सारी कायनात में एक कातिल बीमारी सी हवा हो गई. आई रिपीट, सारी कायनात में एक कातिल बीमारी की हवा हो गई. वक्त ने ऐसे सितम ढाए कि दूरियां भी दवा हो गई. ओके, सो this is the share now. I'll just hear about that. So I just want to share with you. So that's what I'm saying. Stay at home and keep studying, keep motivated here. Okay, so thanks for watching this video. Okay, bye then.